Or
Okay, we can start. Kandu, can you hear me?
I can hear you, absolutely. I can hear you. Yes. We can hear you.
I don't know. I can't hear anybody. I am having problems with my connection here.
Oh, that's annoying.
I'm calling you. Okay, maybe I'll put in.
Okay, Ruth, I will mute my machine.
Okay.
Okay, because for a very long time I couldn't communicate in my machine, and Vasanthi finally tinkered with it and upgraded it. So now you are the first person with whom I am testing whether the two-way communication works, and it does work.
Okay.
No, I thought Ruth is a special person for whose.
No. She is certainly a special person, but that is not the only reason. So I had always tell Kandu that I can't ask questions.
Shamak, we can hear you.
Yeah. Now everything.
We can hear you. I have tried to see. So, do you want to start or? Okay.
But now he's muted. So much.
No, he can't hear us, but we can hear
Shamak's
him.
volume is low. He probably has to hike up the volume.
But he's actually muted.
Hi. Let's start. I'm having problems with my connection, so I hope you can hear me. This is our Thursday colloquium again, and I'm glad to see again a lot of people have turned up, 70 and counting. So let's start. Thank you very much for coming. We have in our Thursday colloquium today Professor Ruth Duder, who's I'm very, very happy to see her here. She's an old friend of IUCAA. I first met her when I was a PhD student in the University in Institute of Astronomy at the University of Cambridge. She was a postdoctoral fellow there. She did her PhD from Zurich, and then went for postdoctoral fellowships at Cambridge, and then Princeton, and then Zurich, and then worked at Zurich for a little while in the 90s before coming to her current position at the University of Geneva. And through her career, she has worked on various interesting aspects of large-scale structure and cosmology, working in the early days with cosmic strings and various topological defects, and then later on moving to inflation, dark energy, all kinds of things. And I mean, people would have seen her recent work on LISA, gravitational waves in cosmological context and stuff like that as well. So wonderful to see Ruth here. I just found out, I've forgotten about this, that it was Ruth's husband who had painted the two large murals that we have on the walls on the Bhaskara lecture theatres. So that's another great connection that Ruth has with IUCAA. So looking forward to your talk, Ruth. Take it away. Thank you.
Thank you very much for the kind introduction, Somak. Thank you for having invited me to this colloquium. Can everybody hear me?
Yes, Ruth, we can hear you.
Okay, very good. So I want to talk to you today about testing general relativity with cosmological large-scale structure observation. I assume this is a colloquium, so I will give an introduction which might be a bit boring for some of you. Oops. Yeah. So I will give a kind of substantial introduction. Then I will talk about galaxy surveys, namely on very large scales and their power spectra. And then I will show in section 4 how we can measure the lensing potential and the gravitational potential actually via galaxy surveys and use these to test general relativity. I will make two very specific examples. One measuring the so-called EG statistics, which would be sensitive to deviations from GR, and one measuring the growth rate of perturbations. And of course, how perturbations grow depends on what is the theory of gravity. As you all know, Einstein's theory has been tested in many ways so far, and it has passed all the tests with flying colors. The first, which made Einstein famous, was a light deflection by the sun. Later on, light deflection by all possible stars and galaxies, etc., via lensing events, which there are thousands in the meantime, but also the perihelion advance, first in Mercury. That was what the first calculation which Einstein actually made about his theory, but later in many other binary systems where the perihelion advance is sometimes not just seconds per century, but degrees per year or stuff like that. We have also measured Shapiro time delays and several other weak field tests and also stronger field tests. And we have lately seen gravitational waves. However, all these observations essentially test the vacuum solutions of Einstein's equation, Ricci equals 0. Can we also test the equations with matter? So when the right-hand side has a non-vanishing energy momentum tensor, there is one situation which we know very well, which is the Friedman Limit solution of cosmology, which is a non-vacuum solution. It assumes that the geometry be especially simple, namely the space-time manifold can be split into space and time, such that the space is a space of constant curvature, so homogeneous and isotropic. And the only dynamical quantity is a scale factor in front of this. And the equations, the first one is actually the cosmological analog of the Radial equation. The constraint tells how the scale factor expands or contracts, is connected to the energy density and a cosmological constant if there is one. And the second is the dynamical equation, which is related to energy density and pressure. Have we not tested already this equation with cosmological observations? Let's think a little bit what we really have measured so far. What we truly have measured is, for example, in the homogeneous universe, the flux from supernovae or other Cepheid variables or so, some stars or some objects, some sources. We have measured the flux from some sources which either have well-known luminosity or for which we have means to get at their luminosity. And if we know their luminosity and we measure the flux, we can infer the so-called luminosity distance. We can also easily measure their redshift Z, and so we can measure the luminosity distance as a function of redshift. In a Friedman universe, this can easily be calculated, and one gets this expression here, 1 plus Z times a function of this kind of radial distance, the integral of the inverse Hubble parameter. And this function can be, depends on the curvature. If curvature vanishes, it's simply the identity. Otherwise, it's a bit more complicated. Is sine square root kr over square root k. That's what we have measured, this dl of c, and let's see what it gives us. Here I show you a figure where the horizontal axis is simply the redshift and the vertical axis is a quantity which is parallel to the logarithm of, which is proportional, pardon, to the logarithm of the distance. It's actually, the so-called distance modulus, and here represented as the logarithm of the distance, luminosity distance, which we measure, divided by the one which we would see in a Milne universe. A Milne universe is a universe with vanishing matter density and only negative curvature, which makes it expand. That would be the zero line here in this plot. And we see that expansion first accelerates and then stops accelerating and probably slightly decelerates. And so, I mean, these dots with error bars here are measured points, mainly from supernovae. There are 870 supernova 1A points, and there are 3 so-called BAO, baryon acoustic oscillation points. I will discuss a bit later how they are measured. That's a compilation from 2017. And you see the blue line here is not a bad fit. And this blue line can be obtained if we assume that 70% of the acceleration today is due to a cosmological constant and 30% is due to matter and there is no curvature. If you assume this, we get this blue line, which is quite a good fit. So no, we have not measured, not tested or the Friedman equations. No, if we want to test an equation, we would have to measure both sides of the equation and see that they are equal. But we measured one side, namely the expansion rate and its derivative, and we inferred from it that we need a cosmological constant, which makes out 70%, and matter, which makes out 30%. And then we can fit the left-hand side of the equations. So we postulated the existence of dark matter and dark energy to fit this data. We didn't measure it. We have measures of dark matter, which give us that omega matter h squared, which should be roughly 0.1, which agrees not bad with this omega matter of 0.3. So with omega matter, things are not so bad. We can, in principle, kind of measure it independently of the expansion rate, independently of these distance measures. But omega lambda, we have no other way to measure it than via geometrical measurements. I mean, I wouldn't know of any other way. Here I show you a little bit more recent compilation of somewhat more supernovae, which tell exactly the same story. I showed you the previous picture because I think it's more illustrative, but this one is a bit newer. But anyway, so what do I want to do in this talk? I want to show you that if we go beyond the homogeneous and isotropic universe and introduce clustering observations, then which use the fact that our universe is not perfectly homogeneous and isotropic, but that there are galaxies, and these galaxies are in clusters and in filaments. And so if we use that, we can actually test Einstein's equations to some extent. We shall do this using a statistical approach, and we are mainly work with the 2-point correlation function, which determines the 2-point correlation function is defined as the probability above or below, if it is negative, the mean of having a second galaxy at the second space-time point position if I have a first one at the given space-time position. That's the definition, and I will go into more details there. What we have done in the past, in the last 10, 15 years, is we have looked at the cosmic microwave background, the relic radiation from the Big Bang, if you want to say so, or the big majority of photons in the universe, which are have a Planck distribution, which are a thermal spectrum at the temperature of about 2.7 Kelvin. And this distribution is very, very homogeneous and isotropic. But if we expand its anisotropy in spherical harmonics, we find, with the assumption of homogeneity and isotropy, we find that the ALMs in this expansion here are only correlated if L and M agree. Otherwise, we would have a preferred direction in the universe. And we have measured this anisotropies and these so-called DLs, which are L times L plus 1 CL divided by 2 pi. And the simplest model with the parameters which I showed you fits very well this data. This simple model, there are 6 parameters which enter in it. These are the omega matter and omega lambda, which I told you about, but also the amplitude and the spectral index of initial perturbations, which generate these fluctuations, and the optical depth to the last scattering surface, and the Hubble parameter. So this data is more or less consists at present our best knowledge about the universe. But it is the data on one hypersurface. It doesn't tell us so much about evolution in Redshift. And if we want to know about the law of gravity, we should know how things evolve, right? And so we try to redo a similar thing with the distribution of galaxies. Oops. Sorry. I don't know whether it does it with you as well. For me now, okay. So here we have the distribution of galaxies as seen by the Sloan data. How can I make this smaller? It doesn't obey me if it doesn't do it. Okay, and people have analyzed that so far mainly by Fourier transforming this. Here, every point on this is a position of a galaxy. So, of course, if we want to interpret this as over densities or so, we have to go from these point process which we see in the universe into an overdensity, and this is the whole problem of biasing, etc., which is a separate problem about which I'm not going to talk a lot during this talk. But in principle, if we can measure these overdensities, people have done this. You know, we can make little bins in Redshift and in angle and convert them into bins, spatial bins, and then assign the number of galaxies in that bin to a number, and then Fourier transform this quantity and get a power spectrum. And that's what people have done so far. And this is, for example, the power spectrum, which is now nearly 10 years old. I just show you this one because here you nicely see the so-called baryon acoustic oscillation, which are the oscillations which you saw in the CMB spectrum are due to the fact that when fluctuations of a given scale enters the horizon, radiation pressure and gravitational attraction make it oscillate. I mean, it starts to collapse until pressure becomes too large and then it expands again. It's really exactly like a sound wave. That's why we call these acoustic oscillations. They are imprinted in the baryon photon fluid, but not in the dark matter. And for this reason, they are very small in the matter power spectrum, because there the baryons are a small 10-15% contribution to the total, which is dominated by the dark matter. But nevertheless, we can calculate very accurately the length scale of these fluctuations. And so we know the angular diameter distance to the last scattering surface, to the redshift at which we observe these fluctuations, because we can measure this length scale very well. And these were the 3 BAOP points which I showed you in the previous graph, the red points. But when we do this, if we want to do really large surveys, we have to take into account that all observations which we make them on our past light cone. That's the only thing we can see, right? So we see, for example, fluctuations which are further away from us, further in the past. We never can observe a space-like hypersurface, but we observe our past light cone, which we actually points on which we actually determine by two angles and the redshift. In cosmology, we cannot measure distances. We can only measure redshifts. But the measured redshift is perturbed by peculiar velocity and by the gravitational potential. And not only the number of galaxies fluctuate due to density growth or so by local gravitational instability, but also the volume is distorted due to perturbations of the geometry. Furthermore, the angles we are looking into are not the angles into which the photons were emitted. They have been lensed on their way to us by foreground structures. For small catalogs, all these effects are not very important. But if we want to go out to redshift of order unity or more, then we have to take such effects into account. So present surveys go already out to redshifts of 0.7 and 0.8, and future surveys will go out to redshifts of order 2 or 3, so we totally will have to take that into account. In a Friedman universe, the radial co-moving distance is just the inverse integral of the Hubble parameter. So you see this result depends not only on H0, but also on the matter content, the curvature, etc. of the universe. Depending on what we measure, if we measure, for example, BOs, we measure the angular diameter distance. If we measure luminosities, we can determine the luminosity distance, or we can directly measure R of C if we measure some radial quantity. All at small redshift, all these distances are simply Z over H0, if the redshift is much, much less than 1. And this uncertainty with H0, we have taken it into account by measuring distances. Our unit of distance in cosmology for this reason is actually H inverse megaparsec, where this little h quantifies the uncertainty of our measurement of this Hubble parameter. But the moment we go out to redshift 1 and beyond, we have to take the full formula into account, and not only the 1 over H0 is relevant, but also the matter density, the cosmological constant, or whatever dark energy we have. So we can no longer just absorb the uncertainty in one number. Let us keep in mind that whenever we convert redshift and angles into a length scale, we make an assumption about the underlying cosmology. Here you see a measured correlation function, which would be a function of, so this is the first thing I want to stress. We can measure the correlation function only on our background light cone. We cannot measure it elsewhere. So, because that's the information we have. So if we measure, so it will depend in general, assuming statistical isotropy, it will depend on the angle between the two directions I'm looking into, and it will depend on the two redshifts of the objects or of the pixels in space, which I correlate. And as this, for example, in a lambda CDM model, if I multiply this correlation function with theta squared, that's how it looks. The moment I convert this into some radial correlation function, I will do something like that and insert these radii or these distances as integrals over the inverse Hubble parameter, which depends on all cosmological parameters. And here you see you get different results depending on what you assume for your cosmology. On very large scales, if you look at the matter fluctuations in the matter distribution, they will depend also on the geometry, because you see matter on your past light cone. This has been studied some 10 years ago, and within linear perturbation theory, the following result was obtained. Let me first just tell you exactly what was calculated. In a galaxy catalog, we have the direction and the redshift of a given galaxy. Now, what we really want to measure or can measure is the following quantity. We can measure inside a small redshift bin and a small solid angle, so in a small pixel, the number of galaxies in there. We can subtract from that the mean of all the galaxies at the given redshift, in the given redshift bin, and divide it by this mean. And then we can correlate, we can look at the correlation function of this object, correlate it with itself in some other direction at some other redshift. And this gives this correlation function, which depends on the angle between the two directions, assuming statistical isotropy, and on the two redshifts. This quantity is directly measurable and therefore gauge invariant within linear perturbation theory. And to calculate it, you have to take into account how photons propagate. You really have to, in first order, solve the photon geodesic equation to know a photon emitted in some direction will arrive at me in some other direction, which is determined by the gravitational potential in between, etc., etc. If you do all this, you get the result which I have written up here. The first term is just the density fluctuation with some bias factor. Here I assume linear biasing, which was always known that, of course, it depends on how the density fluctuates, the local density. Then there are velocity terms, which are from the Doppler effect, coming just from the fact that the longitudinal volume or the redshift volume depends on how galaxies move, depends on the speed of galaxies. Another well-known term is this lensing term here, which is really just a deflection of photons on their way to us. So if you have an overdensity between the two pixels which you look at in the sky, you will have the photons will be slightly deflected, and you see the two pixels further apart, which lets you consider the mean density as less high. So this gives a negative contribution to your overdensity here, this factor, this negative factor. But there is another effect, which is this 5s. The 5 is just, astronomers' definition of magnitudes and stuff like that. Why this factor 5 here comes in, that's the definition of S. But the physics behind this is the following. If you look out with your telescope, you typically have a limiting flux. You can only see objects which have a flux above the limit of your telescope. However, if there is lensing, the flux of certain objects might be enhanced, leading to a larger flux, and so they might make it into your telescope just because in front of them there is some overdensity or there is some large gravitational field, this weak lensing, which is described by this effect here. So this is this term 5s, which enhances the visible overdensity. Then there are other effects which are really relativistic effects. I mean, this here is simply Shapiro time delay, which also comes in to this whole story. This is integrated Sachs-Wolf effect for the photons, etc., etc. This comes from the volume change in the gravitational potential due to the gravitational potential, etc. These are relativistic effects, which are actually quite small. But let me show you one effect which is very well measured, which is the so-called redshift space distortions. Right? If you have, let us assume that here you have some kind of cluster in the middle of this plot here, then galaxies which are in front of this cluster will be drawn towards it. So their redshift for you will look a little bit larger because they are moving a little bit towards that cluster. So you see them more redshifted as the cosmological redshift would be, and the opposite with quantities with galaxies which are behind, you see them less redshifted because they move a little bit more forwards towards that cluster in the center. This squeezes the, if you now convert this smaller redshift difference into a radial distance using the normal cosmological expansion law, this squeezes the structures here into these kind of squeezed onions. However, on small scales, the opposite happens because you have relatively large velocity dispersion inside the cluster. This makes the redshift which you measure very close to the cluster having a larger spread. This produces the so-called fingers of God. Here you see the redshift space distortions as measured in the Boss survey. This is at smaller redshift, and here at slightly larger redshift. So now we have this quantity, this delta, which is again a function of direction, directly observable, and of redshift. We can expand it in spherical harmonics, and again, statistical isotropy requests that only equal L's and M's are correlated, and we get a power spectrum CL, but which now depends on two redshifts. And we can also determine the correlation function, which depends on an angle and two redshifts. Here I show you calculation using linear perturbation theory on a standard universe and showing these different contributions to these CLs at very small redshifts. Redshift only 0.1 and in a very tiny redshift bin. And you see that the dominant term by large is just the density term. All other terms are quite small. Also redshift space distortions are small here because this delta Z is not so tiny. So the redshift space distortions are smeared out over this redshift interval. If you really want to see them, you need to take a delta Z of 10 to the minus 3. Then they come up and are nearly as big as the density effect itself. And all the other terms, the Doppler term or the lensing term, are really, really tiny. However, if you go to higher redshifts, here is the other extreme, redshift 3, and again a very large redshift bin, suddenly the lensing term, which is here shown in magenta, becomes even larger than the density term and becomes, or let's put it like that, it's always of the same order as the density term. And if you neglect it, it's really, things are really wrong. You can also study the radial power spectrum. So how does this CL of C and C prime depend on C prime? If I fix L, here I took 20, and said, how does it depend on C prime? And here in blue, I plotted the so-called standard terms, which are the density and redshift space distortions. They are taken into account by all present surveys, while all the other effects are neglected by all present surveys. And so far, it's reasonably okay to do so. But you see, if you want to correlate different redshifts, lensing will become important and will start to dominate if the redshift difference is big enough. We have looked into this with with for a survey which is roughly corresponds roughly to the Euclid survey by splitting up the full correlation function or power spectrum into a local one, which is dominated by the standard terms, and the integrated contribution, which is dominated by the lensing term. So if one looks at the so the Euclid photometric redshift survey will be able to have roughly 10 redshift bins. If I correlate equal bins, we are completely dominated by the local contribution, so by the standard terms, and the lensing can be totally neglected. However, if we correlate unequal bins, here bin 1 and bin 4, the local terms alone are no longer sufficient to describe the result. And if we correlate far away bins, they are totally dominated by the lensing contribution, and the local one is tiny, is actually not visible at all. So we looked into this and asked ourselves, how well can one, using this effect, really measure the lensing term? And to do that, we just took this lensing term, which is an integral over the two Bardeen potentials, and multiplied it with the term beta. And we asked ourselves, if I simulate the measurement a little bit like lensing, how well can I measure this prefactor beta? We looked at many other cosmological parameters, but let me show you a slightly less busy plot here. What is interesting, if you compare maybe just these 4 variables which we studied, which is this factor beta, which we are most interested in, neutrino mass, the sum of the neutrino masses, the Hubble parameter, and the amplitude of perturbations. The red lines show the analysis if I consider only 5 bins. The black lines, if I consider 10 redshift bins, which is the best I could do. In the dashed lines, we only consider the autocorrelations in the analysis, while in the solid lines, we consider autocorrelation and cross-correlation. And you see all except beta, what is really important is to consider 10 bins. If we consider only 5 bins, the results are not so good. But if we consider 10 bins, whether we consider also the cross correlations or only the autocorrelation, doesn't really matter. The situation is different with beta. Whether we consider 10 bins, the black line, or 5 bins, the red line, is not so important. But it's really important to consider the cross correlations. The autocorrelation error bars or determinations of beta are much worse than those including the cross correlations. And that is exactly the effect which we have seen. Including the cross correlations, we have bin correlations where actually this lensing term is the dominant term and can be really well measured. And so we can test whether the gravitational potential which bends light is really twice the Newtonian potential as general relativity predicts, or whether it is something else. It's not only that. I mean, if we would analyze the photometric catalog of photometric survey of Euclid, neglecting lensing, we would make serious mistakes. Here, I show you again results for cosmological parameter estimations, this time not just using a Fisher matrix approximation where you take derivatives around the simulated values, but really simulating the observations and doing an MCMC analysis, Monte Carlo Markov chain analysis of what you find. And we analyzed the data, which were of course generated with lensing, with the full GR. We analyzed them with lensing in red, without lensing in blue, and using only autocorrelations and without lensing, where we say, okay, in autocorrelations, the lensing is not so important. So maybe that's okay if we neglect it there. And you see what we get. What I find most important, maybe we can just concentrate on that here, is if we assume lensing can be neglected, that the vertical lines are the input lines. If we assume lensing is neglected, then we suddenly see a positive neutrino mass, which is much larger here, 0.3, than what we have put in. Here we have put in the minimal one, which is 0.06 electron volt. And of course, we cannot really distinguish between the bias, the galaxy bias, and the primordial amplitude. So we have this large degeneracy here between the amplitude and the bias. Lensing only depends on the amplitude of fluctuations and does not care whether galaxies are a biased tracer or not, whereas the density, of course, depends on this bias, the visible galaxy density. So clearly this lensing term has to be included also not in order to interpret correctly what we see. An interesting statistics has been developed by Zhang et al. In 2007, which is the following. The gravitational photon propagation is only sensitive to the sum of the body potentials. So these are, in Newtonian physics, this is just twice the Newtonian potential, while non-relativistic particles are accelerated only by the time component of the metric, because their velocities are very small. Non-relativistic density fluctuation, on the other hand, generate the spatial body in potential via the Poisson equation. In GR, these two are identical, but in most other theories of gravity, they are not. So if we can measure them both kind of independently, that would help us to see whether GR is valid. And such a statistics was developed by Zhang et al. And it's, if we can measure this quantity here, we can in principle measure it by looking at correlation between lensing and density divided by the density alone times beta, which relates the density to the velocity. And since density fluctuations are biased, this delta here has a bias factor in both cases. And here it would have a bias factor squared, but beta is proportional to 1 over the bias. So it removes one bias factor here, because here you measure just kind of the redshift-based distortions. And so if you could measure this, and it is constant, independent on redshift and independent of scale, so here independent of the index L, and independent on bias, then this is a good test of GR. But we have pointed out that if you do that, you must really take into account what we actually measure is not the density fluctuation, but it is these galaxy fluctuations, which also has the lensing term in it. And therefore you have to be a bit more careful, and you get a slightly more complicated expression. What you measure is this left-hand side, but you can solve in principle this equation for kappa delta and kappa kappa. And so you can get back the quantities which you truly need, because kappa kappa, you can also measure it with a lensing measurement. So you can solve this and you measure this, so you can subtract it and get CL kappa delta. For low redshifts, this is all not relevant, but if you go to higher redshift, it becomes relevant. If you consider a death-like survey, which already has been analyzed and studied, and which did not take into account these additional terms. We just showed how much this EG statistics was affected from these additional terms. And we found that it was on the percent level. It's for the highest redshift of 0.8, it's about 3 to 4%. But for this high redshift, the error bars are very large, so it doesn't really matter. And for the low redshifts, which are most relevant in this, redshift 0.2 and 0.4, this effect is smaller than 1%, and therefore also for 0.5, it's maximum 1%, so it's not so important. But the next survey will be Euclid, and there, actually, this is redshift 1.5, and this is redshift 2, where it is very important. At redshift 1 for Euclid, it's actually not important, this correction. And the reason for that is, if you look at the expressions, if you look at these expressions, you see that this so-called magnification bias S, if this magnification bias S is exactly 0.4, this term here cancels. And for Euclid at redshift 1, this magnification bias just passes 0.4. And therefore, it's the effect is more or less not there at redshift 1. Another thing which you can think about is if you look at intensity mapping, like for example with SKA, you can show that this term exactly vanishes. This lensing correction term actually exactly vanishes if you are sensitive to surface brightness and not to flux. Because then the increase in the surface is exactly compensated by the increase in the flux. Another thing which we have looked at is the growth rate of perturbations, which is very sensitive to your theory of gravity. A cosmological constant is actually the only form of dark energy which exhibits absolutely no clustering, which is just proportional to the metric. So if you can measure the growth rate, which is more or less the prefactor in redshift space distortion, because the velocities are proportional to the density fluctuations times the growth rate, while the growth rate is the logarithmic derivative of the density fluctuation with respect to redshift or scale factor. So this is very sensitive to it, but for that you need a survey with good redshift resolution to measure them very precisely. So a spectroscopic survey, there the redshift resolution is typically of order 10 to the minus 3 or even better. And what is interesting, we found that even if lensing is not so important for spectroscopic surveys, because their density, in those density fluctuations are really big, it does affect your estimations of the growth rate. Here, this is a different plot, which I showed to you, where on the left-hand side, I show the classical cosmological parameters, the standard cosmological parameters, as they can be determined with LSST. In blue, taking into account lensing, and in red, neglecting lensing. LSST is a photometric survey which will start taking data still this year. Is this Vera Rubin Observatory. It will start taking data still this year. And you see here that taking into account lensing is extremely important. The blue error contours are much smaller than the red ones, especially if you want to disentangle the bias and the amplitude. Since it is a photometric survey, redshift space distortions are not very well measured with this survey. And so you need the lensing to disentangle the bias of galaxy fluctuations with respect to the matter fluctuations. we compared it to a much more futuristic survey, which is this one. This is SKA2. I don't know whether I still will be living when this survey will be present, and that is a spectroscopic survey where lensing for cosmological parameters makes nearly no effect. You see the blue and the red are really not very different. But what is interesting, taking into account lensing, we can, with this much more modest survey, which will start taking data still this year, get nearly as good cosmological parameters as with this very futuristic spectroscopic survey. But one thing we cannot do is measuring the growth rate, and that will be possible with SK2. But also there, once we want to measure the growth rate, we can no longer neglect lensing. Here, the growth rate is plotted with and without lensing. It's not truly the growth rate, it's a growth rate times the amplitude of fluctuations on a scale of 8 megaparsec. And on small redshifts, the error bars are significantly larger than the difference between the orange and the blue curve. But when we go at redshifts above 1, this is no longer the case. Here you see, here we just, for better visibility, we show that the difference from taking into account lensing or not taking it into account divided by the error bar. And you see it's very small at small redshift, becomes a order 0.5 at redshift 1 and becomes larger at higher redshifts. So we will have, if we would take these blue results at face value, then we would conclude from this measurement that GR is ruled out, because we would have taken these three last points together, we would have a 3-4 sigma result that GR would be rolled out, but that would just be because we made the wrong analysis. So it's very important to do things correctly when we will make such amazing measurements, which will come. So let me conclude. So far, cosmological large-scale structure mainly determined the correlation function as a function of distance, or equivalently the power spectrum, or higher order bispectrum, etc., etc. They are easier to measure because they are less noisy. They give you a less long data vector from the data analysis point of view, but they require a fiducial input cosmology to convert redshift and angles into length scale. This complicates especially the parameter, the error bars. Furthermore, it is not, one has to correctly include lensing, otherwise one gets wrong results. And in future, large and precise three-dimensional catalogs like these mentioned here, Euclid, DESI, SKA, or LSST, we will be able to measure the three-dimensional correlation function and spectra directly from the data without any interpretation. These quantities will be more noisy, they will be larger and so, but they also contain more information, right? We measure the matter density on the one hand, but we also measure the velocity via the redshift space distortions and the space-time geometry via lensing. We can therefore in principle determine both the components of the energy momentum tensor via density and velocity, and the geometry which allows us to test Einstein's equation. Especially if we measure the galaxy clustering and its correlation with lensing, we can determine a quite model-independent test of GR via these EG statistics. We can also test the growth rate, but it will be important to correctly include lensing in the analysis in order not to make wrong conclusions. So what I wanted to tell you is just that the observable spectra, or also the bispectrum, they depend sensitively and in several different ways on your theory of gravity, on the growth factor, on the relation between phi and psi, on the matter and baryon densities, and on the velocities. And their measurements provide a new route to estimate cosmological parameters, but that we have already done to some good extent, but especially also to test general relativity on the large cosmological scales and with a non-vanishing energy momentum tensor. Thank you for your attention.
Thanks very much. That was a fantastic talk. Thank you, Ruth. I will now open the floor to, wonderful, open the floor to questions. We have quite a lot of participants, and I'm sure people will have a lot of questions. So can we use the hands up option, which is down there in your reactions part? And wait for your turn. Asim is first with his question. Asim, you're unmuted.
Hello, Ruth. Nice to see you again.
Hi, Asim.
So could you just briefly comment a little bit about primordial non-Gaussianity? Because I guess this will also be a major target for these surveys, and it will be degenerate with the effects you're talking about.
Exactly, exactly. I didn't talk about that at all. This is a point which is not in my slides. I mean, it is to some extent. The thing is, let me see whether I can go back. Yeah, maybe if we look at these expressions here, if you just think Newtonian now for a moment, then you see that the gravitational potentials, they are of order of magnitude k squared, where k is the wave number, sorry, h squared divided by k squared times the density fluctuation. Right. That's just the consequence of the Poisson equation. And the same is true, for example, for these terms, etc., for all these terms. Now, if you have a primordial non-Gaussianity, it will introduce also such a gravitational potential term actually in the power spectrum, which has exactly the same kind of growth if you go to very, very large scales. So these terms will be difficult to disentangle, and it will be absolutely necessary if you want to calculate the power spectrum to take these observational terms, these light cone terms into account to compute the power spectrum, if you want to see whether you have something which might come from primordial non-Gaussianity.
So I guess what you're saying is you would then have to say that we believe in GR, we will make the prediction for GR, account for these terms, and then allow for a primordial non-Gaussianity signal and try to constrain its amplitude.
Exactly. Yeah. Just allow for a primordial non-Gaussianity signal on top. We can easily model that. And then see how sensitive we are to this FNL. And this sensitivity, I mean, there are these estimates that we are sensitive to an FNL of order unity with future large-scale surveys. But of course, these GR effects, there are actually several works underway which want to do exactly this, which have converted this angular power spectra in Fourier space power spectra, which see that the FNL generated by these additional terms is also of order unity. So this should be measured in the future, even if there is no FNL from primordial non-Gaussianity. Maybe for the people, not for us, but maybe for some of the other people. If single field inflation, which is a good fit to present data, is realized in nature, this means that FNL should be substantially less than 1. So if we measure FNL of 1, and we are sure that's really FNL and not something else, then single field inflation is ruled out.
But I was just wondering whether the redshift evolution, for example, of the signal could be useful in breaking this degeneracy. So, so another way of asking is, can you simultaneously test GR and look for FNL?
The answer is yes, but it's going to be difficult. But you're absolutely right. And you know, also, you also have the bispectrum. And the bispectrum is not the same for the GR effects and from a simple local FNL. So it certainly will be important also to use the bispectrum and not only the power spectrum. But I think one can disentangle. The signals are not identical.
Okay, thank you.
But there is some amount of degeneracy.
Thanks.
Great, thanks. That was a great point. Sanjit, unmuted.
Hi, Ruth. Very nice talk. I just, so in one of the slides where you were changing delta to scaled delta and then trying to do the parameter estimation. So there I noticed that the Hubble constant, if you don't consider lensing, was going very low, like something like 61 or 60 or some very low values. So if you had an external measurement of the I think external measurement of the, not this one, another, this one, I think here's
this one?
yeah,
Is it this one?
Yes. Okay. So if you use an external measurement of the Hubble constant, wouldn't you get a much better constraint? For example, here, if you see the gray lines in the Hubble constant, it is going to something like a very low value, like 63 or something.
63 or so, yeah.
Yeah.
That
so
it is of course possible to use other measurements to break degeneracies, but I'm not sure whether you get everything right, whether that would also help you with the neutrino mass. I'm not sure, but it might. I'm not sure. I haven't done it, so I can't really answer your question. It's a good question, but I don't know the answer.
Anybody else? Yes, Surud is next. Surud, go ahead. Surud, go ahead. Yes.
Hello, can you hear me?
Yeah.
Okay. So Ruth, you calculated these effects for the like what happens if you don't account for lensing and try to do a clustering plus lensing kind of analysis with a DES like survey, right? And the effects were like sub% or so. So I'm part of this Subaru Hypersuprime Chem survey, and there, because we are a precursor to LSST, we are already seeing effects like this start to matter.
Seen your paper. Yes, you have actually measured kappa delta, right?
Right. Yeah.
I've seen your paper. Very interesting.
Right. So we are starting to see this effect. So we are still in the process of publishing even the first year results. But already we are finding that we need to account for the fact that the lenses here, spectroscopic lenses that we are using, they get magnified by the same large scale structure. And then the same structure is also affecting the lensing signal.
Wonderful, very nice.
So already we are starting to see effects. It's not just like something which will come in the future. Something
I have seen your paper, and I think there are old papers where they correlated quasars with foreground galaxy surfaces, and they saw some kind of correlation. But I think yours is a new generation, which is now starting, and it was the first paper I've seen on this. Yes.
So there are magnification bias related papers, but then now actually propagating it to cosmological constraints and taking it properly into account while doing the cosmological constraints, that is something that we are still working on. It should be out hopefully soon. But yeah, it's a very interesting point, and it definitely needs to be accounted for. Thanks.
Thank you. That was an interesting contribution. Great.
Wonderful. Great. Thanks. Who's next? Sharvari is next. I've unmuted you.
Hello, can you hear me?
Yes. Go ahead.
Hi, nice talk. I just wanted to ask, in most of these modified gravity theories, the growth rate is scale dependent. So could you comment a little bit upon what are the future prospects for measuring this scale dependence in the growth rate? With bigger surveys, I assume you can do this sort of a scale-wise project.
Yeah.
Thanks.
Now, of course, that will be more difficult if it is scale dependent, but in principle, of course, you can also test this. I cannot really tell you now exactly what's going to happen because, you know, if you have less data to measure a specific quantity, the error bars will increase. So it will be more difficult, but this is certainly also something one should look into. You are right. I haven't done that and I cannot tell you any results which people have obtained, but it's an important point that one also should consider whether one can measure a scale dependence of the growth rate. It will depend on how strong it is and yeah, but this will certainly also be looked into. It's important.
Let's see next, Shantanu Desai is next. Shantanu, you're unmuted.
Yeah, so thank you, Ruth, for a very nice talk. So maybe, so I have two questions, and maybe both these questions are slightly outside the main purview of your talk, but they're still connected to modified gravity and cosmology. So I'll ask. So I guess within the gravitational waves community, there's a whole bunch of literature on testing Chern-Simons gravity using MRIs, I think, but then the motivation of Chern-Simons gravity is to dispense with baryogenesis. But I've never seen any cosmologists get excited by Chern-Simons gravity. So could you just comment on whether we can test this using cosmology or cosmological observations or next generation surveys? So that is my first question. And the most recent paper on this is by Stefan Alexander and Nico Younes, I think, maybe a month ago, or I forget when.
Mm-hmm. Honestly, I have never studied it. I don't know. I can't answer your question. Can you with Chern-Simons gravity also get the correct Hubble diagram, so at least the background?
So, well, again, I'm not an expert. I think there are gravitational wave people in this call, but I think it has an R wedge R Lagrange. It's mainly to I think get leptogenesis and then baryogenesis using the Fukugita-Yanagita mechanism. But again, I'm not an expert. But I just wanted to know if this can be tested using cosmology. I mean, there's obviously a lot.
The little bit I know about it is it's much more relevant for the early universe. So, or for high energies. At low energies, I think it really boils down to GR more or less. So I'm not sure that this would have any effects on these measurements. But I'm honestly, this is just kind of a general impression and not informed answer.
Can I ask one more
question? Yeah, go ahead. Yeah.
Can I ask one more question?
Yes,
again, this is also slightly outside the main purview of your talk, but still connected to modified gravity. So I guess, what about modified theories of gravity which try to solve the Big Bang singularity problem, things like Chern-Simons gravity? Is it possible to again test them with next generation cosmology? So I guess in 2006 and 7, between around 2006, there was a fight on this in Physics Today between Steve Weinberg and Fred Hale. So I'm just curious on what your thoughts on testing, not just Chern-Simons, any other theories of gravity which dispense with Big Bang singularity.
Mm-hmm. There again, my answer is the same. I think no. And the reason is that these theories of gravity, like for example, if you would add just an R² term, which is something where you can make nice inflation and everything, Starobinsky inflation, for example, they have no effect on large scales at late and in late time cosmology because their deviations to GR have completely died at in this low curvature regime we are now. If you would have a 1/r term, then that will become important at low curvature. So yeah, those theories of modified gravity theories which are used to explain dark energy, they can be tested with such observations. But theories which modify gravity in the ultraviolet are not very sensitive to such things because in the infrared they give GR. We know around the solar system scales we should have something which is very close to GR. So these large scale these modified gravity theories, which help us to explain dark energy or the accelerated expansion of the universe, there we always have to be very careful that we screen their effects on scales of the size of the solar system, because their GR has been tested quite well with astrophysical observations.
Okay, thank you.
I think we have a question from Desh. Go ahead. If Ruth is not tired already, let's see what.
No.
Okay, Desh, and then Kandu is on the line. Desh, can I've unmuted you.
Okay, thanks. Great talk. Thanks for particularly making it understandable to a non-expert. I have a basic question to, relating to the early slide that you had where you showed the acceleration, deceleration domains, the variation with respect to redshift. Always such figures have indicated oscillatory behavior of sort. And I wondered whether the proportions of the energy densities have ever been considered to be varying across redshift.
Oops, I wanted to go back to. Are you referring? Are you referring?
Very early on.
Yeah. Something like this?
Yeah, right.
Okay.
So this is less dramatic, but I've seen figures where the undulation about the mean trend were pretty noticeable at times. And I've
yeah, it's possible. This what you see here is a compilation from 860 dots. So it's very pinned. Maybe for this it would be better to look at the next plot, which is this one. So I would say look at the lower plot. Here you see the individual measurements, and the yellow dots are the bin results in some redshift bins. And so you see it is oscillating a bit, but if you look where the individual measurements lie, I wouldn't overinterpret this. But
right.
Of course you can develop theories which do that. I mean, what you can show is the following. You give me a Hubble law, how the H of C should behave, and I invent the potential of a scalar field, which is going to do exactly that. So you can do everything in principle. But here I wouldn't be sufficiently motivated by the oscillations which we see. If I compare them with the individual error bars, they are just unfortunately still quite large.
Yeah, I agree. In this figure, of course, I completely agree with you. They are not.
And that is a bit the state of the art. That's a bit the state of the art. This is this Pantheon compilation. Yeah, okay, it's in the meantime, it's already 3 years old, but I don't think we have many more. With the Vera Rubin observatory, we will make this much more populated, and maybe the error bars will become smaller. And I mean, if it would be oscillating, that would be amazingly interesting.
Yes, of course. Here's also something for the future cosmology surveys. Maybe not the ones you talked about. Yeah, LSST. Kandu, you were next.
Thank you, Ruth. That was very interesting. One thing which, I mean, you are emphasizing the lensing part of everything, right? I mean, so there is already all those weak lensing surveys which measure the shear correlations and all that. They are at different scale. I was a bit confused because there's already some information from that. So
no, they are absolutely not at different scales. I mean, for example, Euclid will measure also the shear. And what is interesting, this will also be interesting. I should have said more about this. You're right. That is probably something which I missed a little bit. Because if we look at my expressions which I had for the EG statistic, there you need to have shear measurements. If you want to measure these, if you want to get at this CL of K delta, you need CL of kappa kappa. And if you believe in GR, then CL of kappa kappa is entirely determined by the shear, right? And so you can get, that's how you get at it. You need the shear measurements. But for example, Euclid will do both. We'll do galaxy overdensities or galaxy number counts and shear. And what is also interesting, this with the lensing, you can really measure kappa, while with the shear, with the galaxy shape measurements, you measure the shear. And the relation between the two is very, very specific in general relativity. We know exactly what the relation between the two is. And if we find something else, that would be very interesting. This would be another way to test GR by measuring kappa and measuring the shear independently.
Yes, okay. Great, interesting. Yes, thank you.
Thanks very much. And I don't think there are any more questions. It's been a very fascinating discussion after a wonderful talk. Thank you. Thanks, everybody. And thank you very much for being with us, Ruth, today.
Thank you for the invitation, and all the best to everybody. Goodbye.
Bye for now. We have we didn't do the Zoom applause thing, but there you are. Wonderful.
Thanks a lot, Ruth.
Thank you.
Okay.